Hello everyone, myself Chaitanya Kumar from Department of Electrical Engineering IIT Madras, and welcome to week 5 of the tutorial sessions of analog electronic circuits. So in this session we mainly dealt with current mirrors, and for the same we will have tutorial today. So we will first of all start with a review of current mirror as to why do we need current mirrors. So as we discussed previously, so let's say uh, we have current controlled current source. Here is R, and we need certain GM from this, and here we apply the input, here we apply the output in a small signal case. So as you can see, so we need to bias the gate of this current control current source in such a way that we can give the required amount of gain, required amount of the transconductance from this transistor. So the one way to actually bias is through voltage biasing. So how does a voltage biasing work? Basically, you have this common source amplifier, and with that you basically connect through a resistor divider to VDD, and you give your input source, you give your input through a coupling capacitor. So this is one way to bias it, but as you can see that in this biasing, as the VDD changes, there is a change in the gate voltage of this transistor, and due to which the GM of this transistor can change, and hence your the gain that this particular block, the common source block, is supplied to then supposed to give, can change. So you want constant current source across the you want a kind of current source which is constant across the complete circuit that you have. Now building many multiple constant current sources is a tough affair. If you want to build, let's say, a current source, and you have to build current source for every other circuit that is there in your chip, that will be tough. So what we basically do is we build one current source that is constant across temperature, or we source that particular current source from outside the IC that you are making, and copy that particular current across the chip. So due to that, so to accomplish that, we need a current mirror. So how does a current mirror works? Basically, we have the basic current mirror that is present with us is the one where we have some current source. So this is a constant current source which can be sourced. So this is ideal current source, let's say, and by ideal we mean that this is a current source that is generated through some technique that its value doesn't moves around with temperature and a process variation. Either it's sourced from an external IC, or it is generated internally also, and we use this current source, we push it into a transistor, to a diode connected transistor. Now this diode connected transistor gives you some develops some volt VGS. Now if the output resistance of this diode connected transistor is infinity, so what will happen is we know that ID is just a function of diode connected transistor, and multiplied by the aspect ratio that this transistor has. So in order to copy it, if we take this particular VGS and apply it to some other transistor inside your chip, you will have the same current that you will see that there is same current that is flowing from that particular transistor as well. So, and depending on let's say if you want to scale up, scale down the current, if you have, let's say, W by L over here, you put alpha W by L over here, then this current will become alpha ID, and this is how you make current mirrors. And as long as this particular ID remains constant and output resistance of the transistors are infinite, in that case basically you can say that your this particular current also will be constant to a fixed value of alpha times ID. So this is how with one good current source, one fixed current source, you can generate its multiple copies and provide it across the circuit to in order to bias the circuit. So how do we use this technique to bias our common source transistor? What we do is the following. So we know that we have generated a VGS. So this basically behaves, this is just a smart battery which can adjust the output voltage in order to keep the current in the transistors across the chip constant. So basically, once we generate this VGS through this diode connected stuff, what we can do is we can supply it to, we can use this VGS in order to bias any other transistor. So we had this current common source amplifier. So in this common source amplifier, in this common source amplifier, we can connect this through a current source. So we can use this VGS directly connected to the gate of the common source amplifier and give our input through a coupling capacitor. And take our output over here. So with this, the VGS based on the process and temperature variation of this particular this transistor, the VGS keeps on varying so that the current that flows through the transistor remains, but still so that the current that flows through the input device remains constant, hence keeping its parameters constant. So this is basically use case of our current sources. Now let's come to another aspect, that what is a bad current source, or what is a bad current mirror. So in the previous example, we assumed that the current mirror that we were making had both the transistors in that current mirror had infinite output resistance. What happens if we have a finite output resistance? For example, it's W by L over here. It's ID that is flowing through this. We have W by L over here, and we connect this to an let's say somehow this is connected to a voltage source of value VD, and we need to find out what value of Ix, this is sorry, let's say this is alpha W by L, what is the value of I alpha? Okay. And here previously we assumed that the output resistance of both the transistors is infinite. In this case we both have some channel length modulation, and that channel length modulation is characterized by lambda. Okay, so let's see what will be the case in this now. So basically how we characterize and both of them, assuming that VD is large enough, assuming VD is greater than VGS minus VT, that means this transistor is in saturation. This transistor will always remain in saturation no matter what, either saturation or cutoff. So this transistor cannot go into triode. So in this case, how will the current and voltage of these two transistors be related? For transistor M1, we will have ID is equal to mu n Cox W by L into some VGS minus VTH whole square times 1 plus lambda VGS. Now here why we have VGS? Because here, since this is a diode connected, M1 is a diode connected transistor, so in this case we have VGS equal to VDS. So we have VGS over here as well, VGS over here. Now what will be the current equation for M2? That is I alpha. This will be alpha times mu n Cox W by L into VGS minus VTH whole square times 1 plus lambda times VD. Okay. So if we just now VGS of transistor M1 and VGS of transistor M2 are the same, because these two are the gates are shorted and the sources are grounded, so the VGS is same. What about VDS? So transistor M1 has VDS equal to VGS, while the transistor M2 has VGS equal to VD. So these two, the VDS of both the transistor is different. Now let's assume this is equation 1 and this is equation 2. If we divide equation 2 by equation 1, what we get is I alpha by ID is equal to alpha mu n Cox W by L times VGS minus VTH. So why this value of alpha come? Because here we have told that the aspect ratio, if the aspect ratio of M1 is W by L, aspect ratio of transistor M2 is alpha times W by L. So from there we get this value of alpha. Hello, Thanpasai.
Sir, good evening, sir.
Good evening. Good evening. So we are discussing right now. I will just give a quick review. We are reviewing current mirrors today. So first of all, we reviewed like why we need current mirrors. Can you do you have any recollection of why do you exactly need current mirrors?
Sir, means we can replicate the same current by using the current biasing.
Correct. So, as we did in one of the initial tutorials, for example, if we have this kind of common source amplifier where we do the voltage biasing, in this case, what will happen is if it, let's say, your VDS is changing, your VGS will change over here, and this can change the current in the input device. Okay. So what you do is you do current biasing, that you generate a VGS that can vary with respect to the process and temperature variation, in order to maintain a constant current through this transistor, and use this VGS to bias rest of the transistors in your circuit. And this is basically a principle on which current mirror works. So your issue is, for example, let's say this is some ID that you either source from an external chip, or you generate through band gap reference generator inside the chip itself. So this is an ID which will not vary across the PVT. Now you want, if let's say, if for each circuit in your system, you will start putting different sources of this ID, then your system will become very big. So what you do is, for a specific area inside your chip, you generate one particular ID which won't vary across PVT, and through the help of current mirror, keep on copying it, and the currents that you copy also don't vary with your temperature and other things, and you get a constant current biasing across your chip. Do you understand?
Yes, sir. Yes, sir.
Yeah. So basically, this was the biasing technique that we saw was robust against your like PVT variations, and hence was better to use. So after that, once we understand why do we need current mirror, so then we were discussing what is a bad current mirror. Let's say there is no channel length modulation. Let's say the channel length is like the channel length like then in that case your current in saturation won't depend on VDS, right? But if there is channel length modulation, in that case, what will happen is your current will basically depend on what VGS you have, that is the gate source voltage you have, as well as what VDS you have. So, if let's say you, even if you put constant like you make the VGS of these two transistors same, but your VDS, depending on where this particular circuit is placed, your VDS can be different from your VGS. So you can have different current, you can have error in current copying. And this is basically what is non-ideality in a current source, in a current mirror. So how were we looking at it? Let's say transistor M1. So let's say there is some channel length modulation of value lambda. So for transistor M2, M1, current ID is being pushed. So this is the current equation. How will you write this current equation? Mu n Cox W by L times VGS minus VTH whole square times 1 plus lambda VGS. Can you explain each of the term that we have in this equation,
Yes, sir.
Talpasai? Yeah,
Yes, sir. Yes, sir.
please explain.
Uh, means it's a diode current, no, sir.
Yeah,
Drain current, sorry, drain current. Okay. Mu and C works. It is process parameter, right?
yeah,
Yeah. Mm. Yeah, VGS and VGS is a voltage that we apply.
yeah.
VTH
No,
is
no. VGS is not the voltage that you apply. ID is the current that you apply, and VGS is the voltage that that gets developed for this diode connector transistor.
yes, sir. Means
Yeah.
VGS and VGS should be same, ignoring the mismatches. So based on the WBL, we can vary the IL current.
The I alpha current, you mean?
Yes, yes, sir.
Yeah.
Yes.
So, if let's say this channel length modulation parameter, that is lambda, was not there,
Hmm.
in that case, your I alpha will be equal to alpha times ID. Okay.
Yes, sir.
But when you have channel length modulation, let's say your I alpha is alpha by 2 mu n C ox W by L times VGS minus VTH whole square times 1 plus lambda VD, where VD is the voltage that is present at the drain of the this particular transistor. You understand?
Yes, sir. Yes, sir. For first equation, you write VGS, sir. 1 by lambda times VDS, right?
No, here this is diode connected transistor. So your VGS and your drain and gate are shorted. So your VGS
Oh.
will be equal to VDS.
Yes, yes, sir. Yes, correct, correct.
Yeah. So you have I alpha is equal to alpha by 2 mu n C ox W by L times VGS minus VTH whole square times 1 plus lambda VD. Okay. So I alpha by ID, if you divide equation 2 by, if you divide equation 1 by equation 2, what you get is I alpha by ID is equal to alpha times mu n C ox W by L times VGS minus VTH whole square times 1 plus lambda VD divided by mu n Cox W by L times VGS minus VTH whole square times 1 plus lambda VGS. Correct?
Yes,
You
sir.
understand?
Yes, sir. It should be
Yeah,
alpha is the factor.
yeah. So basically from here what we get is, so this can be knocked off, this can be knocked off, because VGS of both the transistor is same. So what we get is I alpha is equal to alpha times ID times 1 plus lambda VD divided by 1 plus lambda VGS. Now, can you please tell me what approximations you can apply in this equation? What?
Uh, uh,
Yeah,
means If we means we, in order to approximate I alpha into alpha times of id, sir.
I alpha is equal to.
No, we means if we consider channel length modulation, then it would be present. So it can be reduced by making it a source strain, source degenerated resistance. At that time, one by alpha times of VDS, it can be
No,
reduced.
no, no. That like I'm talking about this particular those things we will get to later.
Hmm.
What improvements we can do. But
Hmm.
what I'm asking is, okay, you tell me what is the relationship between this one and lambda VGS? What is lambda VGS in terms with respect to one? Is it very small? Is it very large? Or is it comparable? What is it?
Very small, sir.
Okay, it is very small.
Hmm.
Okay. So in very small term, like if let's say you have studied binomial expansion, right?
Yes, sir.
So if there is 1 plus alpha to the power n, what can this be written as?
Uh, okay. Means
Approximately.
okay.
Approximately, if alpha is much smaller than 1, so 1
Hmm.
plus alpha to the power n, how can it be written?
Alpha, sir.
Sorry? Uh,
Alpha, alpha.
no, no, no. Alpha is much smaller than 1. So how this term can be written? 1 plus alpha to the power n.
Sir, it should be 1 minus alpha some. I'm not
No, no,
able to
1
recall.
plus n alpha.
Ah, yes, sir. Yes, sir.
You recall binomial theorem?
Ah, yes, sir. 1 plus n alpha square, like that. It will become, no?
Yeah, it will keep on repeating, but since alpha is much smaller than 1, so alpha square will be even smaller, and hence the latter terms can be neglected.
Yes, sir.
Okay,
Correct.
so the same thing we will apply over here. What is there? Okay, we shouldn't have, let's say this is alpha 1. It's not alpha because alpha we have used over here. So
Mm.
I alpha is equal to alpha times ID times 1 plus lambda VD times 1 plus lambda VGS to the power minus 1. Okay.
Yes, sir.
Okay. Now in this equation, can you apply this and write it as 1 minus your n here, n equal to minus 1. So
Yes,
this
sir.
equation can be written as 1 minus lambda times VGS, right?
Yes, sir. Exactly.
Okay. And you have 1 plus lambda times VD over here, and
Mm.
alpha times ID is equal to your I alpha. Okay.
Mm.
Okay. Now alpha times ID into 1 plus lambda VD minus VGS plus, sorry, minus
Minus lambda
alpha
square.
square VD VGS. Okay. Now, since your lambda is anyways a very small term, so it's square. Multiplication of two very small quantities will result in even smaller quantity, right?
Yes, sir. We can
So
ignore lambda
this
square.
particular term can be ignored. So what you have at the end is alpha ID plus lambda times alpha ID times VD minus VGS. So essentially, what is VD minus VGS? If you go on top, so VGS was the drain source voltage of the original the biasing transistor, the diode connected transistor, and VD is the drain source voltage of the transistor on in which we are supposed to push the current. So your VD minus VGS is basically difference in the drain source voltage that these two transistors have. Okay, you
Yes, sir.
understand?
Yes, sir.
So what you have over here is alpha ID plus lambda times alpha ID times delta VDS. Okay.
Mm. Mm.
Now, what is this lambda times alpha ID?
Okay. Lambda is channel length modulation parameter, right?
Yeah.
Lambda is one. Alpha is okay. Sir, lambda we can write it as a 1
Okay, okay,
by.
okay. You tell you say this way.
Hmm.
Let's say this was this was like this. You had ID being pushed over here, and you had this setup, and there is some external circuit that is placed in on the top of this. So as you, if let's say channel length modulation wasn't there, in that case your this let's say this is w by l, and this was alpha times w by l. So if channel length modulation was not there, then here the current will be alpha times id, right?
Yes, sir.
And how do you calculate the output resistance of a transistor? It's like you can do the derivation, but at the end of derivation, the output resistance of the transistor comes out to be 1 by lambda times id. 1 by
Hmm.
lambda times whatever current is flowing in that transistor, nominal current.
Yes, sir.
Okay.
Yes, sir.
So in this case, the nominal current is alpha times id, and you have lambda. So basically, this particular term is equal to 1 by r naught, correct?
Yes, sir.
You understand?
Yes, sir. Yes, sir. Correct.
Yeah,
Considering channel and the modulation, yes.
yeah, considering channel and modulation. So basically what you get at the end is your I alpha is alpha times id plus delta vds by r naught. Okay.
Sir, into yeah, alpha is that right?
No, but see, like alpha id was only the current that was going to flow from here, right? The nominal current
Uh,
was alpha id.
yes, sir. Yes, sir. Correct. Correct. Yeah.
Yeah. R naught is the output resistance of this transistor, not the output resistance of this transistor.
Hmm.
Get it?
Yes, sir. Yes, sir.
Okay, so we see that if in conclusion, like as far as small signal changes in small changes in the drain source voltage of this transistor is concerned, this particular current source can be modeled as the constant current that is of alpha id in parallel to an output resistance R naught equal to 1 by lambda times alpha id. Correct.
Yes, sir.
Now, if there is if there is some there is VGS at this node, and this particular node will be connected to VGS. So if there is VGS only at this node, then there will be no current flowing through R naught. That means VGS of this transistor and VGS of the original diode connected transistor is same. So in that case, the current that will be flowing from here will be alpha ID. And if there is anything apart from VGS, you understand?
Yes, sir.
If there is anything apart from VGS, let's say VD, in that case, there will be this current that will be flowing from here is VD minus VGS by R naught, that is equal to delta VDS by R naught. And so overall current that will be flowing from this current source will be alpha ID, that was the original current, plus delta VDS divided by R naught. You understand? Hello?
Sir, we can include this current as well, right?
Which current?
Uh, 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 okay, alpha ID. Okay, okay. Yes, sir. Yes, sir. Correct, correct. Same
Okay.
current, right?
So now, how to solve this problem? What did you see that if there is any voltage that is different at this node, like if the like instead of VGS is there, if there is any other voltage at this node, then there is a problem. Correct.
Hmm.
So how can you solve this?
Sir, while making VD small, sir.
You by making the VD not VD delta VDS small. So
Ah,
basically,
yes.
yeah, you want to match the like you have you have matched the gate source voltage of these two transistors, but you also need to match the gate drain source voltage of these two transistors. If you succeed in doing so, then you will say that okay, you have achieved like then the current the error in current copying will be reduced greatly. Correct.
Yes, sir.
So what you can do is you had VGS over here, ID. So VGS is made, right? Now you need to fix this particular voltage also to VGS, correct?
Yes, sir.
Okay, so how will you do it?
Sir, I mean, if you make it diode connected, then it is a direct way. Then VDS and VGS should be same.
No, but if you make it diode connected, then the whole purpose of then again you can't use this particular thing to then the if you make it diode connected, then what will happen is your see what is the like property of a current source? The current source output resistance. What should the current source of an output resistance be?
Mm. Yeah, that is lambda times of ID, right?
No, but ideally what it should be?
Oh, infinity, infinity. Yeah,
Infinity. If you diode connect it over here, what will be the looking in resistance from this node?
1 by GM.
What is 1 by GM?
Oh, yeah, it is very small. No? Yeah, it is very big,
Very
sir.
small, correct?
Uh,
So you can't do that. What you will do is, let's say if I put an additional transistor over here, okay,
mm,
and I make this voltage, I want to make this particular voltage as VGS, right?
mm. Oh, so
Okay,
in order to make this, we can bias the cascode transistor accordingly, sir. We can do that.
yeah. What value you should put at this node, the gate of this voltage?
Yes, sir. It should be Vs plus uh, means there is calculation also. Gate voltage should be
Okay, what
V
is the nominal current that is flowing through this?
ID, sir.
Not ID. It's basically it's W by L. It's alpha W by L.
Yeah, yeah, alpha times W by L. That the based on the diode current equation, then we can calculate the
It's alpha
gate.
ID.
Yes, sir.
Okay, alpha ID is flowing through this. Okay, now
Mm,
if this transistor and this transistor are nominally equal, so what will
mm,
happen is whatever VGS develops across this particular transistor will be
mm,
approximately same as the VGS that developed on the upper transistor, right?
yes, sir.
Okay,
Because source is not like that. So same gate voltage as same drain voltage. So it should be sir, correct.
okay. So now what will you do? Now let's say this particular transistor has some. So if this is VGS,
Mm,
if this is VGS, what should and a VGS will be developed across this particular transistor as well. So what should be the gate voltage of this transistor?
sir, it should be V bias voltage of transistor will be VGS plus VTH, sir.
VGS plus VGS.
Ah,
This will
yes,
be
sir.
one more VGS. So here you need to
Um,
put two VGS. Okay.
mm, mm,
Now if this VGA now of course due to channel and modulation of this and this transistor being different, there will be slight difference between VGS of this transistor and VGS of the lower transistor, but that difference won't make this particular node change drastically. So it will be roughly equal to VGS. So if this VGS is there, so now here also drain source and drain gate gate source and drain source voltage are VGS. Here also you somehow make drain source and gate source voltage as VGS, so the current copying will be much more accurate. Okay, now you will take the current output from this particular node. You understand?
yes, sir. Yes, sir.
Okay, Now let's compare these two particular current sources. So one was this current source, and here some VD was applied, and other is this current source with some VD with this particular thing. Then you have one more transistor. Here you put two VGS and you apply VD over here. Now, can you tell me what is the minimum VD? What is VD min that this particular drain voltage can go so that this transistor still in saturation? What will be
Sir,
that
it
voltage?
should be, yeah, it should be VG plus VTH, sir.
Are you sure?
Yes, sir. Then only minimum a pinch of that is VD min, right? VD should be VD should be greater than VGS minus VTH, right?
VD should be greater than VGS minus VTH. So VD
Yes.
min
Mm.
is equal to VGS minus VTH. You
Mm.
understand?
Yes, sir.
Now, what happens over here?
That then a VG should be it should be VG plus VTH.
Sorry?
Then what is the minimum gate voltage should be? It should be VD min plus VTH, no, sir.
I'm talking about the VD. That is the drain voltage. Drain voltage of the which transistor? Like as this VD starts going down, which transistor will go into triode first? Like which will be which of these three transistors? Can this transistor go in triode ever?
No, it never go to triode, sir.
Why?
Because it is a gate and a drain are short circuited, so it will maintain the same voltage. So VD min should be VD and VGS both are same, right? Definitely it should be less than gate voltage
It
should
will
be.
VD will be VDS will always be greater than VGS minus VTH. Okay.
Yes, sir. Yes, sir.
Yeah. Now, can this transistor go in such triode? Will this transistor go into triode first?
Yeah, if a VD is getting reduced means yes, sir.
Out of this transistor, okay. If there is some change in VD, let's say
Mm.
there is some change in VD, uh, the drain voltage of this transistor will change with exact amount VD, right?
Yes, sir.
The drain voltage of this transistor, the change in drain voltage of the lower transistor will be higher, lower, equal than the change in drain voltage of the upper transistor. Can you comment on that?
Sir, if VD is getting changed, first transistor will get into saturation, right? Then upper transistor will enter into triode region compared to lower
Correct.
transistor.
Correct. The change in, let's say VD is going down, the drain voltage of the upper transistor will go down with the same rate, while the drain voltage of the lower transistor will go down at a much lower rate. Correct.
Yes, sir. Yes, sir.
So this transistor can go into triode. Like at what VD this transistor will go into triode, the upper transistor?
Uh, if it is less than I mean so 2 VGS minus VD min is less than 2 VGS minus VTH.
2 VGS minus VTH.
Yes, sir.
So can you see that now what happens is here VD min is only VGS minus VTH, but here VD min has now reduced to 2 VGS minus VTH.
Mm.
You understand?
Yes, sir.
So this is not here, although your current became more accurate, but what drawback has now occurred?
Yeah, here we are increasing the bias voltage of upper transistor.
Here basically the swing that you can get at the output of the current source has also reduced.
Mm.
Okay, so this problem can be alleviated. Can this problem, how can you increase the swing in this particular circuit?
Sir, by
Okay,
reducing the bias voltage, then we can reduce, right?
Yeah,
That is
but
one way.
till what value you can reduce this bias voltage? Let's say this bias voltage I keep on reducing. Till what value can you reduce this bias voltage?
Yeah, VD min. Beyond that, we cannot reduce, right?
VD min of what?
Yeah, 2 VGS minus VTH. If you reduce beyond the,
No, no,
I
no,
mean,
no, no. I'm not talking about VD. So okay, what you actually want to do, the objective is objective in reduce the VD min of second circuit. Okay, this is the first circuit, this is the second circuit. So your objective is to reduce the VD min of the second circuit. What you can do to do that? Why? What is basically limiting the VD min? Basically, let's say there is this particular transistor over here. There is some bias voltage at this node. Till what value its drain voltage can go down?
yeah, VB minus VTH, sir.
VB minus VTH. So what is basically limiting your, what is the bottleneck in reducing your VD min?
Yeah, VB bias voltage, sir.
Bias voltage. What is its bias voltage of this transistor?
Yeah, 2 VGS, right?
So to reduce VD min, what will you do?
Yeah, we can reduce 2 VGS.
You can reduce the 2 VGS. So till what value can you reduce it?
Uh, till VD, I mean, okay, MOSFET.
Okay.
Mm,
Now this value is VB, this
mm,
value is VD. So how low can you take this VB? The current and the nominal current from this transistor is still alpha ID. This transistor still its ID.
mm.
Now this particular voltage is VGS. So and the voltage developed across the upper transistor will still be VGS. Now, to what minimum value you can reduce your VB?
It is 2 times VGS, no, sir.
No, two times VGS was earlier, and then you
Mm,
said in order to reduce the VD min of the
mm,
of this current source, you need to reduce the bias voltage. You need to
mm,
reduce it from two times VGS. Okay.
mm,
Now what I'm asking is, okay, you start reducing the bias voltage from VB.
mm, mm.
Okay, till what value you can reduce it? That's what I'm asking. So if you start reducing this bias voltage,
Mm.
which transistor will go into triode?
Sir, lower transistor will go into triode region, sir.
Correct. So the drain voltage of the lower transistor, what is the drain voltage of the lower transistor?
Yeah, it is nothing but VGS, right?
No, no, no. How is it VGS?
Oh, okay. Yeah, it is VD.
No, how it's VD? VD is the
He,
upper
he,
one.
yes, sir. I mean, here was what and all get to source voltage that gate VG. So VD should be, yeah, VD should be VG plus
The
VTH,
gate,
sir.
sorry,
Yes, sir, it should be VG minus VTH, no, sir. VD min.
the VD min of the lower transistor, you mean, right?
Yes, sir.
It can be VGS minus VTH.
Yes, sir.
Okay. So if this voltage can go minimum up to VGS minus VTH, okay, then
Hmm.
what will be value of VB?
Yeah, then it should be, okay. Yeah, two times of VGS, 2 times of VGS minus two times
Correct.
of,
Two times of VGS minus VTH. So
yes, sir.
so basically now what is VD min now? If VB is equal to two times of VGS minus VTH, what is VD min? That is this particular voltage. VD min is equal to
Yeah, then it should be two. Okay, two times of VGS minus, okay, VTH,
In
VTH will
terms
get
of
cancelled.
VB, what is it? In terms of VB, what is it? VB minus
Yeah, VB minus VTH, sir. Yeah.
VB minus VTH. So what is it
Mm.
in actuality?
Yeah, two times of VGS minus two times of VTH.
Two times of VGS minus two times of VTH. So
Mm.
now you see that from two times of VGS minus VTH, the dmin has now reduced to two times of VGS minus two times of VTH. So now you can get a relatively higher swing, although it won't match the swing limits of this particular thing, but it's still better than what you had previously. Now can you now then there is a problem in this current source. There one more problem has crept up in this current source. Can you identify that?
Means in the current source, sir.
Yeah, in this current source, there is one problem that has crept up. Can you identify that?
Problem. It is not PVT in very immune to PVT.
Why?
Okay. Yeah, it is immune, sir. Current source, right? We are biasing with current source, correct?
Yeah.
Uh,
So, like, what was the first reason that we moved from this circuit to this circuit?
uh, because of the drain voltage, right? Second.
Correct. So you wanted to make the drain voltage of the sorry. You wa- you wanted to make the drain voltage of this transistor and this transistor same. So you move from circuit 1 to circuit 2. But
Mm,
now what you have done, in order to reduce the VB, you have
mm,
made the what is the drain voltage of let's call this M2, let's call this M1. What is the drain voltage of VD? What is VD M2? The drain voltage of transistor M2?
yes, sir. We already VGS minus VTH.
It's VGS minus VTH.
Mm.
What is the drain voltage of transistor M1?
Yeah, it is VGS, sir.
It's VGS.
Mm.
So what is the current I alpha now? It's alpha times ID plus like plus sorry
Yeah.
delta VD minus delta VD by R naught.
Yes, sir.
Okay.
Correct. Mm.
What
Mm.
what is delta VD now?
Delta VD minus, yeah, VD is VGS minus VTH. Okay, it is threshold voltage, sir. Nothing but.
It's threshold voltage.
Mm.
Correct? Minus of
Mm.
threshold.
Yes, sir. Yeah,
Okay.
here
So
we are reducing the current. Yeah,
yeah, alpha ID minus VTH
by or not.
by R naught. So now, initially you said that you wanted less error in the current source, but now again you have introduced error in the current source.
Yes, sir. We are not
Purpose
exactly
is
mirroring the
defeated,
current.
no? And then the your purpose is defeated. So
Yes, sir.
now, okay. So why did you needed to reduce this VB in the first place in order to
Yeah, in order to bias, right? In order to get full swing.
get better swing, not full swing, in order to get
Mm.
better swing.
Ah, yes, sir.
Okay. So now this voltage has come to VGS minus VTH. What you can
Mm.
do to bring back? So if voltage source, if a drain voltage of a transistor M2 has come to VGS minus VTH, what you can
Mm.
do in transistor M1 to again bring again remove this error, this particular error, that is delta VD by R naught error.
Mm.
What change can you make in transistor M1 to remove this particular error?
Yeah, we can increase the VGS, sir, get to source voltage.
How will that help?
Yeah, if we increase the get to source voltage, then we there would be no decrement in the threshold voltage, right? Here, delta VD, it is VGS minus. Okay, both are same, right? Yeah. Sir, or else we can bias a transistor.
So, what was the main problem due to which the main problem due to which error in the current source was creeping up was difference in the drain voltages of two transistors.
Yes, sir.
Correct.
Initially.
Now, you are saying that in transistor M2, you need to have that particular drain voltage, that is VGS minus VTH, in order to get your maximum swing from this current source.
Mm.
Correct. So this
Yes,
is
sir.
non-negotiable now. What can you do in transistor M1 in order to in order to remove the current error altogether? Is you can make the drain of transistor M2 equal to what you have in transistor M1.
Yes, sir. While
Okay.
making this, yeah, we went to cascode.
No, no, M2 is already cascode.
Mm.
You need to put, you need to insert. So basically, what you need to do is you had this, right? This was M1. This is M2. And then you had this transistor which had 2 VGS minus VTH, and then you had VD. And this voltage was, what was this voltage? Sorry,
VGS minus
not 2
VTH.
VGS minus VTH, VGS minus, uh, you had this as, wait a second, VB can go to 2 VGS minus VTH, and yeah, correct. This was 2 VGS minus VTH. This voltage was VGS minus VTH. Correct?
Yes, sir.
What is this voltage?
VGS.
VGS. Now let's say I put a battery over here.
Mm.
What the value of this battery must be in order to make this voltage also as
Threshold voltage, sir. Yeah.
VGS
Yeah.
minus VTH over here. Correct?
Yes. Yes, sir.
What value of this battery must be?
Yeah, VTH it should be.
VTH it should be.
Mm.
Okay. So how I will do it is, so this was 2 VGS minus VTH. This was, let's say, M3, and this was VD. Now, if I place identical M3 over here, then what will this voltage now be?
Sir, it should be, yeah, fine. It should be VGS minus VTH.
This should be VGS minus VTH.
Mm.
This again is VGS minus VTH. Now, is there any problem with this circuit?
Yes, sir. We didn't put current meter gate and drain, right?
Yeah. So, where will you do that now? What you need to do is you need to make sure that this voltage, this VGS, varies so that it can varies in such a way that it can maintain a current of value ID in transistor M1, right?
Mm.
So what you basically have to do is, so let's analyze this particular node. Let's call this node X. Okay. Now let's say IM1 was greater than ID. What will happen? What will happen to voltage of node X?
Yes. Yeah, it will reduce now.
Reduce. Okay.
Hmm.
So what you need to do now, if IM1 is greater than ID, that means VGS is higher than
Hmm.
expected. Okay, you need to reduce this voltage.
Hmm. Yes, sir.
Okay, and you see that when this is happening, automatically Vx is also reducing.
Hmm. Hmm. Yeah.
Okay, and vice versa, if IM1 was less than ID, that means VGS is lower than expected.
Hmm.
Here, VGS is less, needs, sorry, here VGS is high, needs reduction. Here VGS is low, needs increase. So VGS is lower than expected. And on the same hand, what will happen to node X in this case if IM1 is less than ID?
Yeah, voltage will decrease, sir.
Voltage will decrease or increase. IM1 is less than ID.
Yeah, it will decrease, no, sir.
IM1 is this current. This current is being pulled out of node X, and ID is this current. This current is being injected into node X. The current that is being pulled out of a particular node is lesser than the current that is being injected in that particular node. Then what will happen to voltage of that node?
Uh, uh, yeah, sir. Means it will increase, no, sir. I'm not getting clear picture, sir. I'm writing down equation. It is.
Okay, so let's say this is a node with some parasitic capacitance. Okay, I
Hmm.
am pulling a current of IM1 from this,
Okay.
and I am pushing a current of ID on this. Okay,
Hmm.
if ID is greater than IM1, what will be the direction of the current that is flowing towards that capacitor? Will it flow into the capacitor or will it flow outside the capacitor?
Yeah, it will flow into the capacitor, sir.
If current flows into the capacitor, what happens to the voltage of the capacitor?
Yeah, it will charge. It is positive, right? Hmm.
It is positive.
Hmm.
So this voltage will,
Yeah, it is. Yeah, it will increase. Okay.
it will increase. Okay,
Hmm.
so if IM1 is less than ID, this X will
Hmm.
increase. And
Hmm.
on the same time, you also needed to increase VGS.
Hmm. Hmm.
Okay, so if you directly connect it to this, what
Hmm. Hmm.
happens is now this the connection that you needed in order to keep the transistor M1 in negative feedback has been now established. Okay,
Yes, sir. Yes, sir.
so this is how you can make. So now here, both the VD. So in this circuit, let's call this circuit 3. Here, VDS of M1 is equal to VDS of M2. This is checked. That means the current copying will be exact in both M1 and M2. And on the same hand, your VDS min is equal to VGS minus VTH. So again, this is also checked that you can have a lower, like a higher swing at the output of the current source, that is this node. So now this circuit seems to be complete. Now other question is what? How will you generate this 2 VGS minus VTH?
Yes, that depends on the source voltage, right? Right. If we have already source voltage as VGS minus VTH.
No, no. I am saying you need an external battery to generate 2 VGS minus VTH, right?
Ah, yes.
How will you do that? Now, one is that okay, do some resistor divider and put this node to some VG, some like make it roughly equal to VGS minus VTH. but that won't remain VGS minus VTH across yeah, the variation.
Okay.
You need to put some voltage over here that will exactly track this VGS minus VTH and keep it fixed
Yes, sir.
with respect to ID. So, okay, here is ID. What is this voltage?
Yeah, VG, sir. Yeah, VD.
VGS,
Mm.
correct?
Mm.
Now, let's say you had another this thing. This is connected to VD, and you pull some current through this.
Mm.
What will be this voltage?
Yeah. That is VS. Yeah, VS, sir.
Mm-hmm.
Source voltage.
Wait. Um, just a minute.
Mm.
So basically, you need to generate, sorry, two VGS minus VTH you need to generate, right?
Yes, sir.
Okay. So this is VGS. If you have a battery that will give you VGS minus VTH, then you will have over here two VGS minus VTH, right?
Mm. Yes, sir.
Okay. Now the question is, how will you generate this VGS minus VTH battery?
Sir, by connecting one more MOSFET, right? Uh,
Okay. So you need to connect one more MOSFET over here.
mm.
How will you connect that?
Yeah, gate. Sir, same. Here, a gate is connected. MOSFET. Okay, writing down. Yeah, it is connected to the gate terminal. This terminal.
Sorry, come again.
Yeah, it is connected to the VGS terminal, sir. Other end, right side. Right.
Let's say you have one more this thing over here.
Mm.
Okay. So now what happens is, what should be the VGS of this particular guy?
Yeah, it should be VGS, right? Okay.
Okay.
Sir, it should be VD.
Okay. Wait. So let's say this is one MOSFET with
Mm.
current ID flowing through it,
Mm.
and its aspect ratio is W by L. Okay.
Mm.
Then there is this other MOSFET with the same current ID flowing through it, but its
Mm.
aspect ratio is alpha times W by L.
Mm.
Okay. Now, if let's say your ID is equal to, in this case, so let's call this M1, let's call this transistor M2. Okay. If ID is equal to, for first, for M1, what you have is uh, mu n half mu n Cox W
W
by
by V.
L times VGS minus VTH whole
Yeah, 1
squared.
by lambda times. Yeah.
Let's forget about 1 by lambda for now.
Mm.
And M2 is ID equal to half mu n Cox W by L alpha W by L times VGS2 minus VTH whole squared. Right?
Yes, sir.
This is equation 1. This is equation 2. Okay.
Yes, sir.
Now what happens is, if you equate these two equations, what do you get is VGS minus VTH whole squared is equal to alpha times VGS2 minus VTH whole squared. Okay, so now you have VGS minus VTH is
Square root
equal
of
to
alpha.
square root alpha VGS2 minus square root alpha VTH. Correct?
Yes, sir.
So you have over here VGS
VGS1 is equal to, yeah.
is equal to,
Uh, Square root of alpha times VGS2. Yeah, we can make separate it and
you have over here 1 minus square root of alpha times
mm,
VTH
mm,
is equal to, here is square root alpha again, and by square root alpha is equal to VGS 2. Okay,
mm.
okay.
Yes, sir.
So at this node, you are expecting 2 VGS minus VTH, let's say. And
Mm.
from here to here, you have VGS. Okay,
Yes, sir.
okay. From here to here, you have VGS. And from here to here, you have basically this particular value. So you at the end, ultimately, you have VGS plus 1 by square root of alpha times VGS minus 1 minus square root of alpha by root alpha times VTH is equal to 2 VGS minus VTH. Correct?
Mm. Yes, sir.
So you can find the value of alpha that you need.
Yes, sir. We can find.
What will that be? So
Yeah. It should to it should when it go. Yeah, VGS
1
minus
by
VTH.
square root of alpha VGS minus
Mm.
1 by square root of alpha minus 1 times VTH
Yeah,
is equal,
VGS minus VTH.
um wait a
Uh,
minute, just a minute. So okay, let's try some different approach over here. Let's try it this way. Let's say this is connected to VDD. You have some value of VGS over here. Now what is this voltage? Let's say this is ID, this is ID. Okay, so
yes.
uh, and this is some alpha times, this is W by L, this is alpha W by L. Okay, so what will be the value of this voltage? Can you tell? VGS minus VGS2. If this is M1, this is M2, this will be VGS minus VGS2, correct?
Yes, sir. Uh, means,
Sorry, this is M1, this is M2. So
yes,
you
sir.
have VGS minus VGS2 over here,
Yes,
right?
sir. Means for M1 it is VGS.
If
Yeah,
M1,
it should be.
yeah, so you will have VGS minus VGS2 over here. What will be the value of VGS2?
Yeah, it should be VGS.
VGS2, how you can calculate is basically ID is equal to half for a transistor M1, ID is equal to half mu n Cox W by L times VGS minus VTH whole squared. And for transistor 2, ID is equal to half mu n Cox W by L times alpha times VGS2 minus VTH whole squared. Okay. So
Mm.
if you divide these two equations, what you get is
Yeah, it should be alpha times. Yeah.
what is it?
Yeah, yes, sir. It should be alpha times of VGS2 by VTH equal to VGS minus VTH.
Alpha times
Yeah, VGS2
VGS2 minus VTH
whole square
whole
equal
square
to
is equal to VGS minus
yes.
VTH whole squared.
Yeah, yes, sir.
Okay. So VGS2 you get as VGS minus VTH by square root alpha
Mm,
plus VTH. Correct?
exactly. Yes, sir.
Okay. So uh, now let's say alpha is equal to 4.
Mm,
Okay. Or okay, we will put the value of alpha later. So what is this voltage now?
yeah, we already finished. Yeah, VG minus. Okay.
VGS minus VTH. So basically this is
Yeah,
VGS minus
VGS minus VTH by root 2 plus
VGS
VTH
minus VTH by square root alpha
plus VTH.
plus, not
Yeah,
plus,
minus VT minus
minus.
VTH.
Okay.
Fine, sir. Yeah.
So this is equal to VGS minus VTH by square root alpha. Okay. You get this?
Yeah, sir. After calculating the right.
Yeah.
Okay.
So after calculating, you will have this.
Mm, okay.
Now, so we will write it cleanly over here. This is the voltage that you get at this node. Okay. Now let's say alpha is equal to okay. Mm, now let's say alpha is equal to 4. Okay. So what you will get at this particular node? Wait just a minute. Okay, we will. I will. We'll take a look later on this particular problem of how to generate this 2 VGS minus VTH. We will take a look on this in next week. I am a little. Even I
Uh,
am a little confused with the circuit.
oh,
Okay,
fine,
so
sir.
for now, let's move on to other problem. We will put this problem for the latitude.
Sure, sir. Yes, sir.
Okay. So now till now we have seen that how to build a current source which basically replicates the current that we need from the replicates the current without any error and has a reasonably higher current swing, right?
Yes, sir.
Okay. So now other problem that can occur in a current source is the problem of mismatch, right?
Mm. Yes, sir.
So
You gave me an idea of how that voltage is getting decreased, sir.
sorry.
You gave me an idea how that voltage, because of mismatch, will current will be vary, but I don't know the actual reason how in equation from in
Yeah, yeah,
mathematical
we will
analysis.
get to that.
Mm.
That's what we are getting at. So
Mm.
let's take the circuit 3 only for our analysis. So this voltage is 2 VGS minus VTH, and here we have connected it to. This is the situation right now. Okay. Now this is transistor M1, this is M2, this is M3, this is M4. Now let's say there is some a mismatch in transistor M3 and M4. Will it have any impact in the current that is current copy?
Yes, definitely it will impact in the current copy because of
Yeah.
yeah, small.
Okay. So if there is mismatch in transistor M3 and M4, here there will be some let's call the you know the sigma of the mismatch, right? Let's say there is mismatch in the talk about only the mismatch in the threshold voltages. Okay.
Mm.
So let's say there is mismatch in VTH of M3 comma M4. Okay. So
Yeah,
if
then
this is
it should be VTH by R naught, that
VGS
current.
minus, if this is VGS minus VTH,
Mm.
so this particular voltage will be some VGS1. This particular voltage will be some VGS2. Okay. What will be difference between what will be VGS1 minus VGS2? Okay, not let's not call it VGS1. So let's call it VD1 and VD2. What is VD1?
Yeah, VD1 is nothing but, yeah,
2
two times.
VGS minus VTH
Mm.
minus VGS3, right?
Ah, yes, sir. Yes, 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 correct. Mm.
Okay. VD2 is 2 VGS minus VTH minus VGS2. Sorry, VGS4. Okay. You understand?
Yes, sir, VD2 should be VGS minus VGS2 minus VTH only, right?
No, no, this is 2 VGS minus VTS. The gate is connected at that, and let's assume that the nominal current that is flowing through this is still the nominal current is still alpha times ID. Okay. If let's say this was alpha W by L and this was alpha W by L, the nominal current is still alpha times ID. We need to see that how much deviation from this nominal current happens. So, if the nominal current is still alpha times ID, so the VGS that will be developed across transistor M4 will be more or less equal to more or less. If there the nominal current that is equal to alpha times ID, then there will be some VGS that will be developed across this M4, right? Some nominal VGS, and we are calling it VGS4. That's it.
Yes, sir. I get. Yeah.
Okay. So VD1 is two, like this is the gate voltage, that is 2 VGS minus VTH minus VGS3, and VD2 is 2 VGS minus VTH minus VGS4. So what is delta VD? That is the difference
Yeah.
between two drain voltages.
Yes, sir. It should be VGS3 minus VGS4.
This should be equal to VGS3 minus VGS4.
Mm.
Okay. So can you tell me what is the different what is the what is VGS3 minus VGS4?
Yeah, it should be okay. Uh,
Okay, what is the overdrive of transistor M3? Let's call the transistor M3's overdrive as VOV3,
mm.
and let's call the transistor M4 overdrive as VOV4.
Oh, yes, sir. It should be 2 times of VGS minus 2
No,
times
no.
of VTH.
Okay, V like nominally VOV4 will be equal to VOV3. This you agree or not? Can you see that?
Ah, yes, sir. Definitely. Both gate are, yeah.
Both gates are connected. The current density flowing through transistor M4 and M3 are same. So
Mm.
we overdrive voltages will are nominally same. So
Mm.
overdrive voltages will be nominally same, right?
Mm. Yes, sir.
So what will be VGS3 then? That will be VOV3 plus
Mm.
VTH3. And what will be VGS4?
Yeah, it should be VOV4 plus VTH4. Mm.
VOV4 plus
Mm.
VTH4. Okay. So what is delta VD?
Yeah, VGS3. Yeah, okay. VO3. Yeah.
VOV. Now this minus this, VOV3 and VOV4 are nominally equal.
Mm.
So what will be delta VD? Delta VD will be equal to VTH3 minus VTH4.
4. Ah,
That
yeah.
is equal to delta VTH.
Mm.
Okay. If delta VD is this, then what is the error in the current? What is the final current that I alpha? That was alpha times ID plus
Mm.
delta VD by R naught, right?
Yes, sir. Yes, sir.
That is equal to alpha times ID plus delta VTH by
By
R
or
naught.
not.
Okay.
Mm.
So this is basically mismatch in. This is the effect of this is the effect of mismatch in M3 and M4.
Yes, sir. Here current is increasing. In the previous case, what we have taken, current is decreasing.
Yeah,
Mm.
no, that will depend basically on the sign of VTH. If delta VTH, if delta VTH is smaller, if delta VTH is negative, it will reduce. If delta VTH is positive, it will increase. The error, the absolute value of error is delta VTH, modulus or delta VTH by R naught. Okay.
Mm.
Now let's assume other case. This is ID. This is VD. This is connected like this. It's like this. Okay. Now this was M3, M4, M1 and M2. Okay. The other cases, let's say there is a difference in this is VTH1 and this is VTH2. This case, the difference is in threshold voltage of transistor 1 and transistor 2. The previous case was that transistor 1 transistor 2 had identical threshold voltage and there was mismatch only in threshold voltages of transistor 3 and transistor 4. In this case, it's ulta. Okay. Now, in this case, what will happen is, okay, the nominal current is still alpha times ID. This is alpha W by L. This is alpha W by L. This is W by L. And this is W by L. So, for the transistor M1, you will have ID is equal to half mu1 Cox W by L times VGS VGS1 minus the VGS of these two transistors are same, right?
Yes, sir.
Yeah, VGS minus VTH1 whole square. Okay, and in the other case, it's I alpha times half mu1 Cox W by L times VGS minus VTH2 whole square. Okay, so if we put it, if we divide these two, what we get is ID minus I alpha is equal to these things will be cancelled. You have just a minute, or we need to find the error in the this thing, right? So what we'll do is we'll do alpha minus ID, that is equal to half mu1, this is alpha over here, half mu1 Cox W by L times VGS minus VTH whole squared minus alpha times VTH1 minus VGS minus VTH2 whole squared. Okay. Alpha is over here. Okay. So you can open this equation. What you get over here is orbit. We shouldn't do it like this. We should first of all multiply it over here with alpha, and then subtract. So then what you will have is VGS minus VTH2 whole squared minus VGS minus VTH1 whole squared, right? So this is half mu1 Cox W by L times alpha times VGS. So if you subtract this, what will you get?
Sir, it should be V. Yeah, it should be VGS VGS minus, yeah,
So
VGS2 VGS1 minus VGS2, right?
no, VGS is same for both. So just open it, VGS square plus VTH squared minus 2 VGS VTH this is 2, this is 2, minus VGS squared minus VTH1 squared plus 2 VGS minus VTH1. Okay, so this is equal to half mu n Cox W by L times alpha. So VGS squared can be cancelled. You have VTH2 whole square minus VTH1 whole square minus uh,
We can
2
write it 2 V
VTS
plus.
VTH2 minus VTH1. Correct?
Yes, sir.
Okay. Now let's say
We can
VTH2 equal to
common.
VTH1 plus delta VT. Okay.
Sir, here we can take VTH2 minus VTH1 common, sir. VTH2, we can write it
Correct.
as VTH2. Yeah.
What you can do is this thing can be written as VTH. What is A square minus B square?
Yeah, A plus B minus A minus B.
A plus B into A minus B.
Yes, sir.
Okay. So from here, what you get is half mu n Cox W by L times alpha times VTH1 minus VTH2 minus VTH1 into yeah, VTH1 plus VTH2 minus 2 VGS into VTH1 minus VTH2. Okay, so from here VTH1 minus VTH2, VTH2 minus VTH1 can be taken common, right?
Yes, sir. We can take it VH2 common, then we substitute the equation. It would be very.
Yeah. So mu n Cox W by L times alpha times VTH2 minus VTH1 times, it's what is it? VTH1 plus VTH2 minus 2 VGS. Okay. Now VTH1 plus VTH2 can be roughly written as 2 VTH. Like there will be some delta VT, but with respect to VTH, that delta VT will be much smaller. So this can be roughly written as 2 VTH. Can you see that?
Yes, sir. Yes, sir.
Okay. So what you have over here is, now this is delta VT. So you have minus of mu n Cox W by L times alpha times VGS minus VTH times delta VT. Okay. So this I have written as 2 VTH. This was 2 minus 2 VGS. So minus 2 I have taken common. Minus 2 will be cancelled with half to just give minus, and then mu n Cox W by L times alpha times VGS minus VTH times delta VT. Do you get this?
Yes, sir.
So this is basically your I alpha minus ID. Okay. Now over here, can you see that? Okay, this is the equation that you get when there is mismatch in these two transistors. Okay. Now we will write down the summary over here. M3, M4. M1, M2, here it's VD, and we are pushing in ID. Okay, so I alpha will be equal to, so if we apply superposition and we consider mismatch of both M3 and M4 and mismatch of M1 and M2, what we get is alpha times ID plus delta VT34. So delta VT34 is mismatch of threshold between transistor M3 and M4. Okay,
by or not.
by R0 minus, what is this term?
GM.
GM, correct?
Mm.
GM times GM of which transistor?
GM of I think it should be
Mu
M2, M2, right?
W by L times alpha into VGS minus VTH.
Mm. Yes.
Which transistors GM this is?
Yeah, it is M4, sir. I think M4, M4.
Okay, M4 and
M3.
not M3. M3's GM will, so this is alpha W by L, this is alpha W by L,
Oh
this is
yeah,
W
M4
by,
and yeah.
this is W by L. So this is GM2, GM of transistor M2.
Yes, sir.
Okay, GM2 times delta
Delta V.
VT 1 comma 2. So can you tell which mismatch delta VT 3 comma 4 by R naught, which of these two will be a higher term? Considering delta VT 3 comma 4 and delta VT 1 comma 2 are equal, now which of these will be a more severe term?
Yeah, it should be R0, sir.
No, which is a larger term? This is this larger or is this larger?
Delta VT3 comma 4 it will be a larger.
No, a delta VT 3 comma 4 is equal to delta VT 1 comma 2. Now,
Yeah.
term 1 will be larger or term 2 will be larger?
Yeah, R0 is nothing but it depends on the lambda times of on A into D, right?
Is 1 by R naught high or is
Mm.
GM high?
Yeah, 1 by lambda R0 will be high, I think.
1 by R naught will be higher, is it?
Yes, sir, compared to GM.
Right? What is
Because
GM2 into R naught? Is GM2 into R naught like a high number or a low number? Like typically for a transistor, GM2 into R naught is like what kind of number?
gain. Yeah, gain. It should nothing
Right?
but gain.
This is much higher than 1.
Yes.
That means GM2 is much higher than 1 by R naught, correct?
Yeah, fine, correct.
So which of the two terms is higher?
Yeah, nothing but second term would be higher.
Second term will be higher. So it
Mm.
goes to say that mismatch in the lower transistor is a much severe problem than the mismatch in the upper transistor.
Yes, sir. Right.
Let's say if there was same degree of mismatch in the lower transistor and the upper transistor, the mismatch of the lower transistor will be a much severe problem.
Exactly.
You get this?
Yes, sir.
Now, you know how to reduce the mismatches?
Yes, sir. Means we need to bias lower transistor such that we can compensate that mismatch.
Okay, that degeneration and all, forget about the degeneration. What is the sigma of delta VT? The standard deviation of delta VT. You know that it's basically some constant divided by square root WL. You know about this concept?
Yes, sir. You thought in circuit. Yeah. But I'm not able to recall exactly now.
Okay,
Uh,
this is basically beyond the scope of this particular subject, so we won't deal in this. But yeah, at least the take home message you can take from this is the mismatch of transistor M1 and M2. Mismatch between transistor M1 and M2 is a much severe problem than mismatch between transistor M3 and M4. Generally, what we do is to reduce the mismatch, we will increase the W into L of the transistors. So, generally, what we do is the W by L of the lower transistor, we keep it W into L of the lower transistor, we keep it much higher than the W into L of the upper transistor, so that the mismatch in the current, the error in the current due to mismatch of threshold voltage is like prevented.
Exactly, sir. Yes, sir.
Okay. So any doubt till here? I will biasing of this particular node, that is 2 VGS minus VTH, we will take up in the next tutorial session.
Yes, sir. Sure, sir.
Yeah, about apart from this, any doubt?
No, sir. I will ask next week. Yeah.
Okay.
Sir, sir, could you give any source? Means I'm getting confused over a while finding the negative feedback. We need to consider signs, right? We need to
Yes.
take care of op amp signs. Either it should be inverting or non-inverting. I'm getting confused on this topic. Could you recommend any book or any tutorial, sir?
So, for this, basically, what you can do is, so there are many circuits of this op-amp based negative feedback so you are talking about the op-amp based negative feedback or negative feedback in transistor circuits?
Yeah, in both, sir.
So for the op-amp based negative feedbacks, you can refer to circuit analysis by Hyatt and Kemerly. So there you will find many problems of op-amp based negative feedback, and you can try to find the signs and all those things. In this thing, Razavi can have the problems for this thing, but whatever circuit you encounter, let's say you encounter a set of circuits in Razavi. So in
Hmm.
Razavi, what you can do is you can try to apply the same principle. For example, you break the node at some particular high impedance point, and say that okay, if you, let's say, this value tries to go up, then this value tries to go down because this is common source. You can uh, now you can basically take the circuits from Razavi and try to see check for negative feedback in those circuits.
Sure, sir. I mean, I'm getting confused. Yeah, next week I work on it, and if I get any stuck or specific questions, I will
Okay,
let you.
so
We'll discuss.
yeah, you can you try to pick circuits from Razavi and try to see how you will identify negative feedback in that. If there is some issue, you can come back and we will discuss it in the next tutorial.
Yes, sir. Sure, sir. Thank you, sir.
Okay, any other doubt?
No, sir. Fine. Everything is fine.
Okay, so thank you for attending this tutorial session.
Yeah. Thank you, sir. Thank you so much.